Our universe began in a state of impossible chaos. To understand that origin, science needed a revolution, and it came in the form of cosmic inflation. By the end of this story, you will see the cosmos not as a simple explosion, but as a structured, dramatic unfolding with consequences for everything that exists. We will uncover how this theory solved glaring flaws in our old story of the Big Bang, explaining why the universe is so uniform and geometrically flat. But we will also confront the profound new puzzles it created, from eternal realms of other universes to the unsettling possibility that our entire reality is just one bubble in an infinite foam. How did a single moment of hyper-expansion set the blueprint for every galaxy, star, and planet? And what does it mean if our universe is not unique, but one of countless others? What does a theory that explains everything about our beginnings tell us about what might lie beyond our own cosmic horizon? The old story of the Big Bang was elegant, but it was quietly falling apart. For decades, scientists had a beautiful, simple narrative. The universe began in a state of unimaginable heat and density, then expanded and cooled, allowing matter to form and eventually coalesce into everything we see. Yet, as observations grew sharper, this narrative began to sprout contradictions so severe they threatened to unravel the entire tale. It was as if you had a map that perfectly explained the shape of every continent, but then discovered the map predicted oceans should be boiling hot and mountains should be floating in the sky. The details were catastrophically wrong. 3 problems in particular stood out as cosmic headaches that refused to go away. The first was perhaps the most baffling, known as the horizon problem. Look up at the night sky in 2 completely opposite directions. The light from those regions has been traveling for nearly 14 billion years to reach us. Now here is the puzzle. The cosmic microwave background, that faint afterglow of the Big Bang, shows that these 2 regions on opposite sides of the observable universe have almost exactly the same temperature. But according to the Standard Model, these regions were never in contact. There simply had not been enough time since the beginning for light or heat or any information to travel between them and smooth out any differences. It would be like walking into 2 separate, isolated bakeries on different continents and finding that every single loaf of bread was baked to precisely 78.3 degrees. Without any communication between them, such perfect agreement is not just unlikely, it is impossible. Yet, our universe displayed exactly this kind of impossible uniformity. The second glaring issue was the flatness problem. The equations of general relativity allow for the universe to have one of 3 possible shapes. It could be positively curved like the surface of a sphere, eventually looping back on itself. It could be negatively curved like a saddle, sprawling outward forever. Or it could be perfectly flat like a sheet of paper where parallel lines never meet or diverge. For the universe to be flat, its density had to be precisely balanced at a critical value. A tiny deviation one way or the other in the first moments would have been magnified exponentially over billions of years of expansion. By today, even a minuscule initial imbalance would have resulted in a universe that was dramatically, obviously curved. Yet, every measurement we have, from the cosmic microwave background to the large-scale distribution of galaxies, tells us the universe is flat to an astonishing degree of precision. The old model offered no reason for this perfect, suspicious balance. It simply assumed it, a piece of cosmic fine-tuning that felt more like a magical assumption than a scientific explanation. Finally, there was the problem of structure. The standard hot Big Bang model described a universe that started in a state of near-perfect smoothness and homogeneity. But our universe today is gloriously lumpy. It is filled with galaxies, clusters, and vast cosmic voids. Where did these lumps come from? what planted the initial seeds, the tiny imperfections that gravity could later amplify into the grand tapestry of the cosmos. The old model had no inherent mechanism to create these necessary fluctuations. It gave us a smooth beginning but no way to get to the clumpy, structured present we inhabit. These three problems, the horizon problem, the flatness problem, and the structure problem, were not minor details to be tweaked. They were fundamental failures, screaming that a crucial chapter was missing from the story of our origins. The stage was set not for a minor revision, but for a complete rewrite of the cosmos's first moment. Into this crisis of cosmic contradictions stepped a young physicist named Alan Guth. It was 1979, and Guth was not initially trying to solve the universe's biggest problems. He was deeply immersed in the esoteric world of particle physics, wrestling with the behavior of exotic states of matter in the extreme conditions of the early cosmos. One evening, working late at the Stanford Linear Accelerator Center, a cascade of connections fell into place in his mind. He saw a solution so elegant and powerful that he later described it with a simple, breathtaking phrase, a spectacular realization. What if, Guth asked, the universe had experienced a brief but unimaginably violent growth spurt in its very first moments? This was not the steady, stately expansion of the classic Big Bang. This was something else entirely, a period of exponential hyper-expansion, where spacetime itself stretched faster than the light within it could travel. The engine for this incredible event was a theoretical state of matter called a false vacuum. Think of the universe's energy state like a ball resting in a valley. The lowest, most stable valley is the true vacuum, the quiet, empty space we know today. But Guth proposed that in the first split second after creation, the universe was trapped in a higher valley, a false vacuum. This state possessed a bizarre property. Its energy density did not dilute as space expanded. Instead, this constant, dense energy filled every new bit of spacetime as it was created, generating a repulsive gravitational force of staggering power. This repulsive gravity did not pull things together. It pushed space itself apart, causing it to double in size not over millions of years, but over inconceivably tiny fractions of a second. In one of his notebook entries from that time, Guth scrawled the implications with clear excitement. This scenario, he wrote, could potentially explain the universe's large-scale properties. That modest note understated a revolution. Guth's insight did not merely patch the holes in the old story. It proposed a dynamic, dramatic event that completely rewrote the first chapter of cosmic history. The horizon problem vanished because before inflation, the entire observable universe was once a tiny, subatomic patch that was in perfect thermal contact. Inflation then took that tiny, smooth patch and stretched it to a size larger than our entire visible cosmos, preserving that smoothness across vast distances. The flatness problem was solved because inflation acted like a cosmic magnifying glass on the fabric of spacetime. Imagine taking a tiny, wrinkled section of a balloon's surface and inflating it to the size of a planet. Any small curvature on that original patch would be stretched so immensely that the resulting surface would appear perfectly flat to anyone standing on it. Inflation did precisely that to the geometry of the universe, forcing it into the precise flatness we observe. And most beautifully of all, this violent stretching provided the seeds for all cosmic structure. The false vacuum was not perfectly uniform. At the quantum level, it would have been fizzing with tiny, random fluctuations. As inflation stretched these quantum jitters to astronomical scales, they became the faint fingerprints of density, the slight over-densities and under-densities that would later, under the pull of gravity, become the galaxies and the vast empty voids between them. Guth's spectacular realization transformed our narrative from a simple, hot explosion into a structured, purposeful unfolding. It gave the cosmos a first act of breathtaking drama, setting the stage for everything that would follow. But as with all great revelations, solving old mysteries only open the door to new and even stranger questions. The horizon problem presented a paradox of impossible coordination. How could distant cosmic neighborhoods agree on everything from their temperature to their density when they had never, according to the old timeline, had a chance to meet? Inflation rewrites that timeline with a startlingly simple premise. Before that explosive growth spurt, everything we can now see was not separated by vast gulfs of emptiness. It was all crammed together into a region smaller than a single proton. In that unbelievably dense hot speck, every particle was in constant, intimate contact. Heat could flow freely, energy could balance out, and the entire future contents of our observable universe achieved a state of perfect, smooth equilibrium. They were not strangers destined to be forever apart. They were neighbors sharing the same tiny room. Then, inflation turned on. In that fleeting fraction of a second, the very fabric of space between these neighbors did not just expand, it erupted. That subatomic volume was stretched to a size that dwarfs everything we will ever be able to see. The consequence is profound. 2 points on opposite sides of our sky today, whose light has traveled for nearly 14 billion years to reach us, were once practically touching. Their matching temperatures are not a cosmic coincidence. They are a frozen memory of that ancient closeness. Inflation acts like the ultimate zoom lens on reality. It took a tiny, well-mixed sample of the early universe and magnified it to become our entire cosmic landscape. The large-scale uniformity we observe is not a puzzle to be solved. It is the expected signature of a small, connected beginning that was stretched to cover the heavens. This elegant solution does more than fix a calculation. It changes how we visualize our origins. We are not looking out at disconnected islands of reality. We are seeing the magnified imprint of a single, unified moment, a snapshot of incredible smallness blown up to a scale beyond human comprehension. That perfect smoothness solves one mystery, but it leads directly to another, equally profound question about the shape of space itself. Geometry is not just for textbooks, it is the hidden rulebook of the cosmos, dictating how light travels, how gravity bends, and ultimately, the fate of everything. For our universe, the geometry we measure is a specific and puzzling one. It is almost perfectly flat. This is not a metaphor. In a flat universe, parallel laser beams will never meet or diverge as they cross the cosmos. The angles inside a triangle drawn across galaxies will always add up to exactly 180 degrees. This flatness corresponds to a precise, critical balance between the density of all the matter and energy in the cosmos and the rate of its expansion. And here lies the old model's second great failure, the flatness problem. According to the classic Big Bang, this perfect balance is terrifyingly fragile. Think of trying to balance a pencil perfectly on its point. In the first instance after the beginning, the universe's density had to be tuned to that critical value with an accuracy of 1 part in a number with over 50 zeros. If it was even the tiniest fraction higher, the universe would have collapsed back on itself in a catastrophic crunch almost immediately after it began. If it was the tiniest fraction lower, matter and energy would have diluted so rapidly that stars and galaxies could never have formed. Our very existence seems to depend on a preposterously unlikely, razor's edge beginning. It feels less like physics and more like a miracle written into the cosmos's first line. Inflation removes the need for that miracle by rewriting the entire first paragraph. It acts like the ultimate cosmic iron, taking whatever wrinkled or curved geometry the universe started with and stretching it smooth. Imagine a single, tiny crinkle on the surface of a deflated balloon. Now inflate that balloon to the size of the Earth. From the perspective of an ant walking on that now enormous surface, that original crinkle is gone. The ground beneath its feet appears perfectly, endlessly flat. Inflation does exactly this to spacetime itself. That brief, hyper-accelerated expansion stretches any initial curvature so dramatically that it becomes imperceptible across our entire observable horizon. The flatness we measure with such precision is not a delicate, fine-tuned starting condition we were lucky to have. It is the inevitable, smoothed-out result of that primordial growth spurt. The universe is flat not by miraculous accident, but because inflation made it that way, ironing out the wrinkles of creation and leaving behind the vast, even canvas upon which our cosmic history would later be painted. But solving the horizon and flatness problems was only half the victory. There was a third, more subtle crisis lurking in the equations, one that threatened to derail our entire understanding of the fundamental forces of nature. This was the monopole problem. To understand it, we must step into the world of particle physics, where scientists seek a single, elegant framework that unifies all the forces we know. These grand unified theories, or GUTs, describe a time in the earliest moments of the universe when the forces of electromagnetism and the nuclear forces were not separate, but one and the same. And these theories make a very specific, very bold prediction. In that searing, unified energy, strange and massive particles should have been forged in abundance. They are called magnetic monopoles. Unlike every magnet you have ever seen, which always has both a north and a south pole, a monopole is a hypothetical particle with just one. A solitary north or a solitary south wandering the cosmos. According to the standard hot Big Bang timeline, these exotic relics would have been produced in staggering numbers, as common as protons. They are predicted to be incredibly stable, virtually indestructible, meaning they should still be all around us today. Finding one would be a Nobel Prize-winning discovery. Yet, despite decades of searching in everything from moon rocks to deep-sea sediments, and with sophisticated particle detectors, not a single, definitive magnetic monopole has ever been found. Their complete absence was a glaring contradiction. Either our best theories for unifying physics were fundamentally wrong, or something dramatic happened in the early universe to make these predicted particles vanish. Inflation provided the elegant escape. Remember, inflation was not just an expansion, it was a dilution event of almost incomprehensible scale. Any monopoles that formed before inflation began would have been present in that initial, tiny, subatomic patch. Then inflation turned on, stretching that patch to a size larger than our entire observable universe. The number of monopoles did not change, but the space they occupied exploded by a factor of at least 10 to the 26th power. Imagine taking a single grain of sand and dispersing it evenly throughout the volume of our entire galaxy. The density of that sand becomes so vanishingly small that you would have virtually no chance of ever encountering it. Inflation did precisely this to the monopoles. It swept them away, diluting their density to perhaps one per volume as large as our entire visible cosmos. They are not gone, but they have been scattered into the unimaginable vastness that lies beyond our horizon, effectively rendered undetectable. With one powerful stroke, inflation resolved the conflict. It allowed the beautiful mathematics of grand unified theories to stand, not contradicted by missing cosmic artifacts. It told us that the monopoles are out there, but our local neighborhood has been cleaned of these exotic relics, giving the universe a fresh, smooth slate upon which the ordinary matter of stars and planets could later form. Inflation did not just explain what we see, it explained what we do not see, removing a ghost from the machine of the cosmos. The most astonishing consequence of inflation is not what it smoothed out, but what it left behind. The universe we inhabit is not a featureless void. It is a magnificent tapestry of structure woven with galaxies, clusters, and vast filamentary webs. For decades, the origin of this cosmic architecture was a profound mystery. How did a universe born in a state of near-perfect smoothness become so gloriously, beautifully lumpy? Inflation provided the answer, and in doing so, forged a direct link between the ghostly realm of quantum mechanics and the grand classical cosmos we see today. The key lies in the nature of the Inflaton field itself, that strange energy state that powered the hyper-expansion. At the quantum level, nothing is ever perfectly still or perfectly uniform. Empty space is not empty, it is a seething, bubbling sea of virtual particles flickering in and out of existence. This quantum foam is a fundamental property of reality, a constant, tiny jitter in all fields. During the unimaginably rapid expansion of inflation, something extraordinary happened to these quantum jitters. A tiny fluctuation in the Inflaton field, a region where the energy was a minuscule fraction higher than its surroundings, was caught in the act of stretching. Inflation took that subatomic ripple and, in less than a blink, expanded it to a scale of light years, then millions of light years. The same process happened everywhere, stretching every random quantum fluctuation into a faint, frozen imprint on the fabric of spacetime. These imprints were not fluctuations in temperature or matter yet. They were fluctuations in the very geometry of space, tiny hills and valleys in the gravitational landscape. When inflation ended and the universe transitioned to the more familiar hot Big Bang, these frozen ripples in gravity became the seeds for all future structure. Regions of slightly higher density, those gravitational hills, had a tiny bit more pull. Over the next billions of years, this gentle extra attraction acted like a cosmic gathering point. Dark matter and ordinary matter were drawn toward these seeds, slowly, inexorably building up their mass. What began as a quantum whisper became a gravitational shout, pulling in more and more material, eventually collapsing under its own weight to form the first proto-galaxies, then galaxies, and the immense clusters we observe. This means the majestic spiral of Andromeda, the sprawling Virgo supercluster, and every star in our own night sky can trace their ultimate origin back to random quantum uncertainty, magnified to cosmic proportions by inflation. The theory provides a breathtaking unification of scale. It tells us that the same fundamental rules governing particles in a laboratory also wrote the blueprint for the entire universe. The grand architecture of existence was not preordained, but emerged from a foundation of quantum chance, stretched and sculpted by a single, transformative event at the dawn of time. A powerful scientific theory does more than just explain what we already see. It makes a bold, specific prediction about something we have not yet measured. Inflation's greatest triumph was not merely solving old puzzles, but foretelling the exact pattern of the universe's birthmarks. It predicted that those quantum seeds, stretched to cosmic proportions, would leave a very particular signature on the sky. The pattern is known as a nearly scale-invariant spectrum. In simpler terms, it means the primordial ripples in density should have been roughly the same strength, whether you look at the scale of a single galaxy or a cluster of 1,000 galaxies. This is not an obvious outcome. It is a subtle mathematical fingerprint left by the specific physics of that hyper-expansion. This prediction, often called the Harrison-Zeldovich spectrum, became the ultimate test. Could we find this fingerprint imprinted on the oldest light in the universe? The answer came from the cosmic microwave background, that faint afterglow from when the universe first became transparent. This radiation is not perfectly uniform. It is a tapestry of incredibly tiny temperature variations, mere millionths of a degree, representing the slightly denser and slightly emptier regions from which all structure grew. Mapping these minute fluctuations became the mission of a series of extraordinary space observatories. The Cosmic Background Explorer, or COBE, gave us our first blurry map in the 1990s, revealing the lumps were indeed there. The Wilkinson Microwave Anisotropy Probe, WMAP, provided a sharper image, and the Planck satellite delivered a map of breathtaking precision. What these missions found was a resounding confirmation. The statistical pattern of hot and cold spots across the entire cosmic microwave background matched the predictions of inflationary cosmology with stunning, almost uncanny accuracy. The sizes of the spots, their distribution, their correlations, all pointed back to a universe that began with a specific kind of quantum storm, stretched smooth by an exponential growth spurt. This was not a vague resemblance. It was a detailed match between a theoretical prediction made decades prior and the most ancient photograph of the cosmos ever taken. That observational evidence transformed inflation. It moved the idea from a clever speculative solution to a handful of problems into the foundational pillar of modern cosmology. We now have compelling, data-driven reason to believe that a dramatic inflationary event truly did shape the first moments of everything we know. The universe itself provided the corroborating evidence, etched in the faint glow of its own infancy. Yet for all its explanatory power, inflation demands a driver, a cosmic engine capable of generating such an unimaginable event. That engine is known as the Inflaton field. This is not a particle we can trap in a detector or a force we can feel. It is a theoretical entity, a field of energy that is thought to have permeated all of reality in the first fleeting moments. To understand it, picture a landscape of energy states, like a series of valleys and hills. The lowest, most stable valley represents the quiet, empty space of our universe today, the true vacuum. But the Inflaton field, in that first instant, did not rest there. It was caught in a higher valley, a state physicists call a false vacuum. This was a metastable state, like a ball perched precariously on a high plateau. It could have stayed there, but it was destined to fall. And this false vacuum state held a bizarre and powerful property, negative pressure. In our everyday experience, pressure pushes outward like air in a tire. But this negative pressure had the opposite gravitational effect. Instead of pulling matter together, it generated a fierce, repulsive gravity that pushed the very fabric of space itself apart. This repulsive force was the piston of the cosmic engine. As space expanded, the energy density of this Inflaton field did not dilute. It remained constant, meaning every new bit of space created was filled with the same repulsive energy, which created more space in a runaway, exponential reaction. The universe did not just grow, it doubled in size repeatedly, over intervals so short they defy comprehension. This was the exponential hyper-expansion that defines inflation. But such a state could not last forever. Eventually, through a process akin to radioactive decay, the Inflaton field began to lose its stability. Imagine that ball on the high plateau starting to roll. It rolled down the energy landscape, transitioning from the false vacuum to the true, lower energy vacuum. And when it reached the bottom, it did not stop quietly. All the pent-up energy that had been stored in that false vacuum state, the energy that had been driving the expansion, was released in a tremendous burst. This moment, known as reheating, was the true beginning of the hot Big Bang as we traditionally picture it. That released energy flooded the newly stretched cosmos, reheating it into a seething, dense plasma of particles and radiation. Everything we recognize as matter and energy in our universe, from the quarks that form protons to the photons of light, was born from that grand release. The Inflaton field itself, having done its work, faded from prominence, leaving behind only its echoes in the geometry of space and the seeds of galaxies. The search for the identity of this field is one of the most profound quests in physics today. Is it a completely new, fundamental field unique to the early universe? Or could it be connected to a known field like the Higgs field that gives particles mass? The specific shape of its energy landscape, its potential, determines everything about inflation's character, how long it lasted, how intensely it stretched space, and the precise pattern of the quantum ripples it imprinted. Unlocking the Inflaton's nature would mean understanding not just how our universe began, but why it began with these specific properties, moving us from a compelling story of creation to a complete theory of our cosmic origins. The Inflaton field solved the universe's initial conditions, but in doing so, it may have opened a door to something far stranger. If a single region of spacetime can undergo that explosive, exponential expansion, what is to stop it from happening again, or from never stopping at all? This line of reasoning leads to one of the most profound and controversial ideas in modern cosmology, the inflationary multiverse. In many models, once inflation begins, it becomes eternal. The process does not end everywhere at once. Instead, as the Inflaton field decays in one region to create a bubble of stable, hot universe like our own, the surrounding space continues to inflate at a staggering rate. That surrounding space, still in a false vacuum state, can itself spawn new bubbles which then spawn more in an endless, branching chain reaction. Our entire observable cosmos, with all its hundreds of billions of galaxies, becomes just one bubble in an infinite, frothing sea of cosmic expansion. Each of these bubble universes nucleates with its own random set of conditions, potentially with different values for the fundamental constants of nature. The strength of gravity, the mass of an electron, the very number of spatial dimensions could be different in each one. In this vast cosmic landscape, most bubbles would be stillborn, empty, or unstable, collapsing instantly or expanding into barren voids. But by the sheer law of infinite numbers, some tiny fraction of bubbles would, by random chance, have the precise, delicate balance of constants needed for atoms to form, stars to ignite, and life to eventually arise. We find ourselves in one of those rare, hospitable bubbles, not because the universe was fine-tuned for us, but because we could only ever exist to ask the question in a place that allowed for our existence. This is known as the anthropic principle, a selection effect that replaces cosmic fine-tuning with a statistical necessity. It solves the mystery of our universe's suspiciously perfect parameters by suggesting we are simply the winners of an infinite cosmic lottery. Yet this breathtaking vision creates a new and profound mystery of its own. If these other bubble universes are forever separated from us by ever-expanding walls of inflating spacetime, regions with which we can never exchange light, matter, or any information, then can the multiverse ever be more than a philosophical idea? Can a reality composed of causally disconnected domains ever be subjected to genuine scientific test? Some physicists argue that if certain signatures were imprinted on our cosmic microwave background from a collision with another bubble in the distant past, we might find evidence. Others suggest the very properties of our universe, the specific pattern of its quantum seeds, could hint at the wider landscape from which it grew. But for now, the multiverse remains a plausible, even compelling, consequence of the physics that so elegantly explains our own beginnings, a shadow cast by the light of inflation, pointing toward realms of reality we may never directly see. The multiverse offers an answer to fine-tuning, but it introduces a paradox of its own. If eternal inflation is true, and new bubble universes are constantly being born in an infinite, ever-expanding sea, then every physically possible outcome must occur. Not just once, but an infinite number of times. In this boundless cosmic landscape, there will be an infinite number of universes with stars and planets, and an infinite number that are dark and empty. An infinite number where the laws of physics match our own, and an infinite number where they are wildly different. This leads to a profound mathematical and philosophical headache known as the measure problem. When everything happens an infinite number of times, how do we define what is likely? Probability, the very language of prediction in science, seems to break down. Saying something is more probable usually means it will happen more often in a set of trials. But when the set of all universes is infinite, comparing infinities becomes a treacherous task. It is like trying to determine if there are more even numbers than whole numbers. Both sets are infinite, so how do you compare them? You need a rule, a method for counting, a way to define a proportion within the endlessness. This is the measure, a mathematical scheme to tame the infinite and extract a meaningful sense of odds. Without it, the multiverse explanation risks becoming untestable, a story where anything is possible and therefore nothing is specifically predicted. The problem becomes starkly clear with a concrete example like the cosmological constant, the mysterious energy driving the accelerated expansion of our universe. Its observed value is extraordinarily small, but not zero, a fact that has puzzled physicists for decades. In a multiverse, every conceivable value for this constant should be realized in some bubble. So why do we find ourselves in a universe with this peculiarly tiny number? The anthropic answer would be that only in bubbles with a value very close to ours can galaxies form and life emerge. But to make that a rigorous prediction, we need to know if bubbles with our value are common or incredibly rare within the infinite froth. Are they a frequent fluke in the cosmic foam, or a one in an infinity shot? If we cannot define a way to count the bubbles and compare the sizes of infinite sets, we cannot say. The measure problem thus strikes at the very methodology of cosmology. A powerful theory should not only explain what we see, it should also tell us what we should expect to see. If inflation's most expansive consequence, the multiverse, makes all outcomes equally real across infinity, then it may have explained everything and predicted nothing. Scientists continue to propose possible measures, ways to slice the infinite loaf of reality to get a finite, comparable slice. Some suggest counting only bubbles that have formed by a certain time, or those within a certain causal patch. But no consensus has been reached. This deep challenge reminds us that our quest to understand the origin of our own cosmic home may have led us to the edge of a conceptual abyss, where the tools we forge to explore a single universe tremble before the prospect of limitless others. But this elegant engine of creation comes with its own profound and unanswered question. What turned the key? Inflation masterfully describes what happened once it started, painting a vivid picture of exponential expansion that solves our cosmic puzzles. Yet it remains utterly silent on what set the whole process in motion. What was the universe like in that fleeting instant before inflation began? The theory requires a very specific starting line, a tiny patch of space that was already smooth, already uniform, and already dominated by that peculiar Inflaton field energy. Getting the universe into that perfect, poised state is arguably as difficult a problem as the ones inflation was designed to fix. We have traded the mystery of the Big Bang's initial conditions for the mystery of inflation's initial conditions. It pushes our ultimate question back one step from what caused the hot, dense beginning to what caused the cool, smooth state that allowed for that hyper-expansion to ignite. This leads us into speculative and profound territory. Did our universe emerge from a random quantum fluctuation in a deeper, timeless void, a bubble of something spontaneously appearing from nothing? Or was it born from a cataclysmic collision or a phase transition within a pre-existing cosmos, a new domain budding off from an eternal, larger reality? Our current laws of physics, the very tools we use to understand reality, are built to operate within a universe that has time and space. At the moment of absolute beginning, if such a moment exists, those concepts may lose all meaning. The equations break down, and we are left peering into a conceptual abyss where words like before and cause may no longer apply. The quest to understand what set off inflation forces us to confront the very limits of our knowledge, standing at the edge of the knowable and gazing into the ultimate mystery of existence itself. This elegant solution, however, rests on a hidden assumption, one that pushes our understanding of reality to its absolute breaking point. The quantum seeds that grew into galaxies did not start their journey at a comfortable, familiar size. Inflation stretched them from a realm so inconceivably tiny that our current laws of physics simply do not apply. This is the Trans-Planckian Problem, a deep crack in the foundation of our cosmic story. To grasp it, we need to consider the Planck length, a fundamental scale in nature. It is about 1.6 times 10 to the negative 35 meters, a distance so small that if you enlarged an atom to the size of the observable universe, the Planck length would be roughly the height of a single tree. At this scale, the smooth, continuous fabric of spacetime described by Einstein's general relativity is expected to dissolve into a seething, chaotic foam governed by the unknown laws of quantum gravity. Our entire description of how those primordial quantum fluctuations behaved during inflation relies on a framework called quantum field theory in curved spacetime. This powerful tool treats spacetime as a smooth, classical stage upon which quantum particles dance. But here is the profound issue. The fluctuations that gave rise to our cosmic structure were, for a fleeting instant, smaller than this Planck length. They originated in that foamy, quantum gravitational regime where our trusted equations have no purchase. We are extrapolating our known physics across a boundary into absolute terra incognita. It is as if we had a perfect map for navigating a calm ocean, but we used it to chart a course that began inside a raging, microscopic maelstrom, assuming the map would still hold true once we sailed out into open water. The Trans-Planckian Problem asks a deeply unsettling question. Do we trust that the predictions of inflation, which so beautifully match the cosmic microwave background we see, actually survive this journey from the unknowable? It is possible that new physics at that ultimate scale could have imprinted itself on those fluctuations, subtly altering their character. Perhaps the nearly scale-invariant spectrum we observe is not the pure, unadulterated voice of the Inflaton field, but that voice filtered through the bizarre quantum grain of spacetime itself. This transforms our perspective entirely. The cosmic microwave background is not merely a fossil of inflation. It becomes a potential, if incredibly faint, messenger from the frontier where gravity and quantum mechanics finally unite. The pattern of hot and cold spots on that ancient sky might carry encrypted signatures of quantum gravity, a mystery from the first sliver of time stretched across the entire heavens. Our most successful story of cosmic beginnings, therefore, points directly to our greatest remaining ignorance, inviting us to look deeper into that faded afterglow for clues to a theory of everything. Eternal inflation offers a cosmic vision of endless creation, but it also invites a philosophical nightmare of startling proportions. This nightmare has a name, the Boltzmann brain paradox, and it emerges from a simple, chilling question about what kinds of observers an infinite, eternal reality should logically produce. The thought experiment begins with a principle from 19th century physics, the idea that in a sufficiently vast and random system, even the most wildly improbable events will eventually occur by sheer chance. Given enough time, the random jostling of atoms in a box of gas could, by incredible coincidence, arrange themselves into a complex, self-aware structure with memories and thoughts. Physicist Ludwig Boltzmann first pondered such statistical flukes. In an eternally inflating multiverse, space and time are literally without end. The quantum vacuum fizzes with potential, and over infinite durations, every possible configuration of particles will spontaneously arise not once but an infinite number of times. This means disembodied, self-aware minds could randomly fluctuate into existence from the void, complete with fully formed but entirely false memories of a past life, a universe, a history that never actually happened. These hypothetical entities are what we call Boltzmann brains. Now consider the numbers. In an eternal multiverse, the process of forming a Boltzmann brain through a random quantum fluctuation, while astronomically improbable in any given moment, has infinite time and space to play out. In contrast, the formation of an ordinary observer like you or me through 13.8 billion years of cosmic evolution, galaxy formation, planetary development, and biological evolution, is an immensely complex and lengthy chain of events. The staggering implication is this: in an infinite reality, the number of Boltzmann brains should be infinitely larger than the number of ordinary, evolved observers. If we are just random observers in this multiverse, the statistical probability that you are a Boltzmann brain, a momentary accident with illusory memories, is essentially 100%. This is not a playful thought experiment. It is an epistemic catastrophe, a conclusion that utterly destroys our trust in any reasoning, memory, or scientific observation. If you cannot trust that your past is real, that the world you perceive has any continuity, then all knowledge collapses into doubt. The paradox screams that something in our reasoning has gone terribly wrong. Either our understanding of probabilities in an infinite setting is fundamentally flawed, a reflection of the measure problem we cannot solve, or the premise of eternal inflation itself is incorrect and the multiverse is not eternal. Some physicists suggest a deeper principle of quantum gravity may prevent such bizarre fluctuations, that reality has a kind of cosmic immune system against Boltzmann brains. This unsettling puzzle forces us to confront the strangest implications of our most successful cosmic theory, revealing that the quest to explain our origins may ultimately challenge our very sense of what is real. The Inflaton field solved the cosmic puzzles, but it left behind a question of its own identity. We have been speaking of it as a single, defined entity, but the truth is far more complex. Inflation is not a single, monolithic theory. It is a powerful framework, a general plot for the universe's first act, and within that framework, countless specific scripts can be written. Each script is defined by the precise mathematical shape of the Inflaton field's potential energy, that landscape of hills and valleys we imagined. This shape dictates everything: how long inflation lasts, how violently space stretches, and the exact character of the quantum ripples it imprints. And herein lies a profound new mystery, often called the why that Inflaton problem. Out of an infinite number of possible shapes for that potential, why did our universe have the very specific one that produced the nearly scale-invariant spectrum of fluctuations we observe in the cosmic microwave background? Why that particular script and not any other? This question pushes the frontier of fine-tuning to an even deeper level. We are no longer just asking why the cosmological constant is a certain value or why the universe is flat. We are asking why the very laws of physics, or at least the specific inflationary law that set our cosmos in motion, are what they are. Enter one of the most ambitious theories in fundamental physics, string theory. In its quest to unify all forces, string theory suggests something staggering: that there is not one unique vacuum state, one true lowest energy valley, but a vast, perhaps infinite, array of possibilities. Physicists call this the landscape of vacua. Each point in this landscape represents a different stable configuration of the extra dimensions and fields string theory describes, and each corresponds to a different set of effective laws of physics and constants in the universe that would emerge from it. The numbers involved are almost impossible to grasp. Some estimates suggest there could be 10 to the power of 500 distinct possible vacuum states. That is a 1 followed by 500 zeros, a number so vast it dwarfs the number of atoms in our observable universe. In this context, the Inflaton field that drove our cosmic inflation is not a singular, predestined actor. It is merely one possibility among an unimaginable multitude. Our specific inflationary potential, the one that gave us our nearly flat, structured cosmos, becomes just one entry in a cosmic catalogue of stupefying size. This reframes the ultimate question entirely. The mystery shifts from why do we have these laws of physics to what selected our particular point in the landscape. Was it a random quantum roll of the dice, a single chance outcome frozen into reality? Does the anthropic principle apply here as well, meaning we only find ourselves in a universe whose inflationary potential allowed for galaxies and life, making our observation a selection effect rather than a fundamental fact? Or is there a deeper guiding principle, perhaps a law of quantum gravity or a theory of the initial conditions, that uniquely picks out the potential we experienced? For now, this remains one of the most open and profound questions at the intersection of cosmology and fundamental physics. It suggests that understanding our own universe's birth may require us to map not just its history, but the contours of an entire hidden multiverse of mathematical possibility, a landscape where every law of nature might be written, waiting for its moment to unfold. The cosmic microwave background is a powerful testament, but it is an echo, an indirect imprint of that first cataclysm. For a theory as foundational as inflation, scientists yearn for something more direct, a signature written not just in light, but in the very fabric of reality itself. They seek a smoking gun, a prediction so unique to inflation that its discovery would be an undeniable confirmation. The most promising candidate is a whisper from the dawn of time, a ripple in the architecture of the cosmos known as primordial gravitational waves. Imagine the universe in that first violent moment of hyper-expansion. Such a convulsive event would not have been smooth. It would have sent tremors through spacetime itself, creating gravitational waves, literal waves in the geometry of reality, propagating outward from the birth of everything. These are not the gravitational waves we detect today from colliding black holes, which are recent and local events. These would be primordial, fossilized ripples from the inflationary epoch, stretched to wavelengths that could span the entire observable universe. Their detection would be a direct line back to the first fraction of a second, and they would leave a very specific fingerprint on the cosmic microwave background, a subtle, swirling pattern in the polarization of that ancient light, known as B-mode polarization. Finding this curly signature in the sky would be one of the greatest discoveries in the history of science. It would be like finding the inventor's signature etched onto the cornerstone of creation. Teams of researchers have mounted extraordinary efforts to find it, using telescopes at the South Pole like BICEP and Keck, places where the cold, dry air offers a crystal-clear view of the cosmic background. Their results have been profound, but not in the way many hoped. They have not found the signal. Instead, they have placed ever tighter limits, constraining the possible energy scale of inflation and ruling out some of the simplest, most elegant models. The silence is itself a message, telling us that if inflation happened, it might have been at a lower energy or involved more complex physics than we first imagined. This elusive search pushes scientists to other frontiers. Could the large-scale structure of the universe, the precise arrangement of galaxies and voids, hide subtle imprints of those primordial ripples? Could future particle accelerators, probing to ever higher energies, recreate conditions that hint at the Inflaton field's properties? For now, the lack of a definitive, direct detection means that while inflation stands as the leading, most compelling framework we have, it is not yet conclusively proven. This is not a weakness of science, but its greatest strength. It leaves the door open for bold alternatives, for other ideas about how the universe could have begun. It maintains a healthy, creative tension at the very frontier of cosmology, a reminder that our story of origins, for all its beauty and explanatory power, remains a chapter we are still actively writing. The search for a smoking gun keeps cosmology honest, because inflation's dominance is not a monopoly on truth. For all its elegant solutions, it is not the only conceivable story for our cosmic dawn. A healthy scientific landscape thrives on competition, on the existence of viable alternatives that challenge the front-runner and force it to prove its worth. Several compelling theories have emerged, each proposing a radically different first chapter that still aims to solve the same puzzles of flatness, uniformity, and structure. One of the most intriguing is the ekpyrotic model, named from the ancient Greek word for conflagration. In this vision, our Big Bang was not an explosion from a singular point, but a rebirth from a collision. Picture our three-dimensional universe as a membrane or brain floating in a higher dimensional space. In the cyclic version of this idea, another parallel brain slowly approaches ours over eons. When they finally collide, the immense kinetic energy is converted into the heat and radiation of a new cosmic beginning. This collision replaces the inflationary epoch with a preceding phase of slow, gentle contraction, smoothing out the universe and setting the stage for the bounce. Here, the horizon problem is solved not by hyper-expansion, but because the entire observable universe emerges from a tiny, causally connected region in the contracting phase. The flatness problem is addressed by the smoothing nature of that slow contraction, and the quantum fluctuations of fields during the collision can still seed the large-scale structure we see. It is a cosmic phoenix narrative where the universe undergoes endless cycles of contraction, collision, and expansion. Other alternatives venture into even more speculative territory. What if the speed of light was not a constant in the fiery early universe? Theories of variable speed of light propose that light traveled vastly faster in the first moments, allowing distant regions to communicate and achieve thermal equilibrium without the need for inflationary stretching. The horizon problem melts away because light had time to connect everything. Modified gravity theories, which tweak Einstein's equations under extreme conditions, also attempt to reshape the early universe's dynamics to naturally produce the smooth, flat cosmos we observe. These are not mere thought experiments. They are full-fledged, mathematically rigorous frameworks that make specific, testable predictions. Crucially, many of these alternatives predict a very different pattern of primordial gravitational waves than standard inflation does. Some, like the simplest ekpyrotic models, predict an undetectably weak signal, a stark contrast to the strong B-mode signature many inflationary models hope to find. The cosmic microwave background itself might hold subtle statistical clues, different imprints left by quantum fluctuations born from a bounce versus a rapid stretch. This competition is not a sign of weakness in cosmology. It is its greatest strength. The existence of viable alternatives provides the essential testing ground. It transforms inflation from an untouchable dogma into a hypothesis that must constantly defend its title. Every new, more precise map of the cosmic microwave background, every more sensitive search for gravitational waves, becomes a high-stakes experiment that can discriminate between these grand narratives of Genesis. This means that inflation, for all its breathtaking explanatory power and its remarkable fit with current data, is not the final answer. It is our current best-fit model, the story that most elegantly weaves together the evidence we have in hand. Its ultimate fate, whether it will be validated as the true prologue to our universe or replaced by a more profound narrative, rests entirely on the shoulders of future observations. The silence in the gravitational wave detectors so far is already shaping the debate, ruling out entire families of simple inflationary models and giving breathing room to the challengers. This ongoing quest reminds us that the origin of everything is not a settled fact in a textbook, but a living, breathing mystery at the very frontier of human understanding, where our best ideas must continually prove themselves against the unforgiving testimony of the cosmos itself. The echoes of that first great acceleration may still be shaping our cosmos today. We live in an era where the universe is not just expanding, but its expansion is speeding up, driven by the mysterious force we call dark energy. The mechanism behind this modern acceleration bears a haunting, mathematical resemblance to the engine of cosmic inflation. Both phenomena appear to be driven by a form of energy that exerts a negative pressure, generating a repulsive kind of gravity that pushes space itself apart. This parallel is so striking it forces a profound question upon us. Are inflation and dark energy two faces of the same cosmic entity, a single underlying phenomenon that acted with unimaginable ferocity at the universe's birth and has now reawakened in a far gentler form to guide its old age? Or is this similarity just a breathtaking coincidence, a trick of the mathematics with no deeper connection? The implications are staggering. If they are linked, it would mean the force that set the cosmic blueprint in the first split second is the same force that now determines the universe's ultimate fate. It would weave the entire story of the cosmos, from its explosive beginning to its distant, fading end, into a single, unified narrative. Some theoretical frameworks attempt to do exactly this. They propose a dynamic field, sometimes called quintessence, that could have powered the violent expansion of inflation, then settled into a dormant, low-energy state for billions of years. As the universe expanded and matter diluted, this dormant field's influence could have gradually re-emerged, taking over as the dominant component of the cosmos and beginning the present epoch of acceleration we call dark energy. In this view, the universe's two great accelerations are not separate events, but chapters in the life story of one persistent, shaping presence. Solving this mystery is more than an academic exercise. It could provide the key to a unified description of the universe's behavior at its most extreme scales, connecting the first instant of time to the final shape of eternity. It asks us to consider whether the cosmos has a kind of memory, a persistent thread woven through its entire history, whispering that the beginning and the end are intimately, fundamentally connected. This smooth beginning crafted by inflation hides a deep and unsettling mystery about information itself. Think about that tiny, subatomic patch that was stretched into our entire cosmos. It contained a specific set of quantum information, the exact arrangement of every field and fluctuation. According to our current laws of physics, particularly in quantum mechanics, information is never truly lost. It can be scrambled, transformed, or hidden, but it must in principle be recoverable. This is a sacred principle, yet inflation seems to have taken that precious initial data and stretched it far beyond our cosmic horizon. From our vantage point inside this bubble universe, that foundational information is now irretrievably gone, spread across distances light can never cross. It creates a cosmic-scale version of the famous black hole information paradox. Did inflation permanently erase the universe's birth certificate? This is not a trivial puzzle. If the information describing our initial state is truly lost, it challenges the bedrock of quantum theory and suggests our understanding of reality is incomplete at the most fundamental level. Some physicists look to a radical idea for a solution, the holographic principle. It proposes that all the information contained within a volume of space, like our universe, is not spread throughout its interior but is instead encoded on its two-dimensional boundary, like a cosmic hologram. Applying this mind-bending concept to the entire inflationary cosmos is a monumental challenge, but it offers a tantalizing possibility. Perhaps the information of our primordial patch was not lost, but faithfully projected onto the distant, unreachable surface of our bubble. We cannot access it, but in principle it remains. This shifts the problem from loss to encryption, a cosmic code written on the walls of reality. Even more profound than the fate of information is the question of time's origin. Did the universe have a definite beginning, a first moment where time itself flickered into existence, or could it be eternal, stretching infinitely into the past? Inflation offers intriguing paths for both answers. In some models, the process of eternal inflation has no starting point. Each bubble universe, like ours, has a finite history within it. But the larger multiverse of inflating space has always been and always will be an endless cycle of creation without a creator. In this view, our Big Bang is not the absolute beginning, but a local event within an ageless meta-reality. Other models suggest our universe burst forth from a quantum tunneling event, a spontaneous leap from nothingness, or from a prior state of timeless geometry. This quantum genesis would represent a true beginning, but one where the classical idea of a singular point of infinite density is replaced by a smooth, probabilistic emergence. Here, the question of what came before loses its meaning, as time itself is part of the emergent reality. These are not just philosophical musings, they are active frontiers of quantum gravity research, where theories like loop quantum cosmology propose a bounce that replaces the singularity, and string theory landscapes paint pictures of eternal potential. Inflation, by so elegantly setting the stage for our universe, forces us to stare directly into the void and ask what, if anything, stood behind the curtain. It compels us to redefine what we even mean by a beginning, blurring the line between physics and metaphysics, and reminding us that our greatest cosmic story may still be missing its very first word. Ironically, the very mechanism designed to eliminate cosmic fine-tuning may require its own delicate balancing act. Inflation masterfully explains why our universe is so flat and uniform, freeing us from the need for a miraculously precise starting point. Yet, to perform this cosmic magic trick, many specific models of inflation demand that their own internal parameters be set with a suspiciously exact precision. The heart of the issue lies in the shape of the inflaton field's potential, that energy landscape we visualized, for inflation to last long enough to stretch a subatomic speck into our entire cosmos, and to produce the nearly scale-invariant spectrum of fluctuations we observe. That potential must be exceptionally flat. Not just a gentle slope, but a plateau of incredible smoothness over a vast distance. In the language of particle physics, such a flat potential is considered unnatural. Fields naturally want to roll down into valleys to find stability. A perfectly flat plateau, maintained across an enormous range, feels like balancing a marble on a vast, polished tabletop with no grooves or dips to guide it. Any reasonable quantum correction, any interaction with other fields, should introduce bumps and wrinkles that would ruin the smooth expansion, ending inflation too quickly or creating the wrong pattern of cosmic seeds. So we are left with a curious puzzle. Have we truly solved the fine-tuning of the Big Bang, or have we simply traded a cosmic fine-tuning problem for a particle physics fine-tuning problem? Critics of inflation point to this as a fundamental weakness, suggesting the theory merely relocates the mystery rather than resolving it. Its proponents, however, see this not as a failure but as a vital clue. The unnatural flatness of the inflaton potential might be a signpost pointing toward deeper physics we have yet to uncover, perhaps within a more complete framework like string theory or a theory of quantum gravity. Such a flat potential emerges naturally from the mathematics. It could be the inevitable outcome of certain symmetries or the dynamics of extra dimensions. In this view, the fine-tuning is not an arbitrary accident, but a logical consequence of a richer, hidden structure. This pushes our quest into even more profound territory. We are no longer just asking how our universe began. We are asking why the laws of physics permitted a story with this specific prologue at all. The mystery of inflation's own parameters becomes a gateway, challenging us to look beyond the inflaton itself and into the fundamental principles that could make such a graceful beginning not just possible but necessary. The cold, geometric perfection of inflation could not last. For all its power to stretch and smooth the cosmos, the inflaton field was trapped in a false state, a temporary plateau of energy destined to fall. And when it finally fell, the universe did not wake gently. It erupted. This pivotal moment is known as reheating, and it marks the violent birth of the cosmos as we traditionally imagine it, a seething, chaotic fireball. Think of inflation as winding up a cosmic spring, storing immense energy in the stretched fabric of space itself. Reheating is the moment that spring was released all at once. As the Inflaton field rolled down its energy landscape and oscillated around its true minimum, it did not simply fade away, it decayed, and in doing so, it transferred virtually all of its pent-up energy into a raging storm of new particles. This was not a slow leak, but a catastrophic cascade. In a flash, the cold, nearly empty vacuum of the inflationary epoch was flooded with matter and radiation. The temperature of the universe, which had plummeted to almost absolute zero during the hyper-expansion, rocketed upward in an instant to temperatures so high they are almost meaningless, perhaps 1 billion times hotter than the core of our Sun. The universe became a dense, opaque plasma of fundamental particles, quarks, gluons, leptons, all colliding and interacting at energies we can only dream of recreating in particle accelerators. This is the true beginning of the hot Big Bang, the moment the cosmic clock of thermal history started ticking. Yet for its monumental importance, the Reheating Era remains one of the most poorly understood chapters in our story. The physics is fiendishly complex, moving from the smooth, classical expansion of inflation into the turbulent, quantum-dominated process of particle creation. Scientists believe reheating was likely driven by a phenomenon called parametric resonance. Imagine pushing a child on a swing. If you push at just the right moment in each swing, the amplitude grows and grows. The oscillating Inflaton field acted like that perfect, rhythmic push on other quantum fields. Certain particle species would have been caught in this resonance, their production exploding in intense, non-linear bursts rather than a steady trickle. It was a turbulent, chaotic phase, perhaps lasting only a fraction of a second, but it set the entire table for what came next. The efficiency and temperature of reheating determined the initial conditions for the next great cosmic event, Big Bang nucleosynthesis, which forged the first light elements. It dictated the initial abundances of particles and antiparticles, setting the stage for the matter-dominated universe we live in. The specific details of how reheating unfolded could have left faint echoes that might still be detectable today. The violent, resonant bursts may have generated a unique secondary spectrum of gravitational waves, a fainter chorus beneath the primordial roar from inflation itself. The process could also have produced exotic, stable relic particles that might now form part of the mysterious dark matter that shapes our galaxies. Understanding reheating is therefore not just an academic exercise. It is the essential bridge, the missing link that connects the elegant, smooth geometry of inflation to the rich, complex, particle-filled universe that followed. It transforms our narrative from a story of abstract fields and expansion into a story of concrete creation, the moment when the cold, silent blueprint of the cosmos was finally filled with the heat, light, and substance of everything to come. The flow of time from past to future feels as fundamental as gravity. Yet physics tells us this arrow is not built into the equations. It emerges from a single, profound condition. The universe began in a state of extraordinary order. For over a century, the origin of that pristine starting point was cosmology's deepest thermodynamic mystery. Why was the early cosmos so improbably smooth and arranged? Inflation offers a breathtaking answer, one that ties the direction of time itself to that first violent stretch. The key lies in a concept called entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy in a closed system always increases or at best stays the same. This relentless rise is what gives time its one-way direction, from order to disorder, from a structured past to a randomized future. But for this law to drive the arrow, the universe needed a starting line of fantastically low entropy. Think of a new deck of cards perfectly ordered by suit and rank. Shuffle it once and it becomes slightly more disordered. shuffle it 1,000 times, and it reaches a state of maximum randomness. Our universe today is like a partially shuffled deck, but the early universe was that pristine, ordered new deck. The question has always been who dealt that perfect hand. Inflation provides the dealer. In the moments before inflation, the entire observable universe was compressed into a subatomic patch. For a region that unimaginably small, even a hot, dense plasma represents a state of maximum possible entropy. It is as shuffled and disordered as that tiny space can get. Then inflation ignited. In a flash, that tiny patch was stretched to a size larger than everything we can see. This did not just enlarge space, it exploded the ceiling for possible disorder. The maximum possible entropy for a region is proportional to its volume. By inflating the volume by a factor of trillions upon trillions, inflation raised the maximum entropy to a number so vast it is meaningless. Suddenly, the actual entropy of the universe, which was at its maximum for the tiny pre-inflationary patch, became vanishingly small compared to the new, colossal maximum. The universe was left in a state of profound thermodynamic imbalance, a condition of incredibly low entropy relative to what was now possible. This is the cosmic equivalent of taking a single, well-mixed drop of ink and releasing it into a suddenly created ocean. Relative to the ocean's capacity for dilution, that drop represents an extraordinarily ordered, low-entropy starting point. From that moment on, the universe had only one thermodynamic path available to climb toward that new, distant maximum. This climb is the increase in entropy that drives the arrow of time. Every process we associate with time's flow, from the cooling of your coffee to the fusion of stars, is a step on this long journey from inflation's imposed order toward ultimate disorder. The smooth, uniform early universe revealed by the cosmic microwave background was not a puzzling anomaly. It was the direct, frozen signature of that low-entropy boundary condition. Inflation did not merely create space, it wound up the cosmic clock, setting it ticking forward by creating a staggering gap between how things were and how they could possibly be. In this view, the relentless flow of time, the very experience of before and after, is not a primitive feature of reality but an emergent legacy, a thermodynamic echo of that first great expansion that has been ringing through the cosmos for nearly 14 billion years. That silent, foamy realm beneath the Planck scale may have left its mark after all. While inflation elegantly explains the large-scale patterns we see, it also provides an extraordinary opportunity. The cosmic microwave background is not just a fossil of the Inflaton field, it is a colossal detector, a screen upon which the deepest laws of physics might have projected their first, faint signature. The detailed statistics of those temperature fluctuations hold secrets that go beyond inflation itself. They could contain whispers from the era of quantum gravity. Most inflationary models predict that the primordial seeds should follow a very specific, smooth statistical pattern known as Gaussian statistics, and they should be nearly scale-invariant. But what if the violent marriage of quantum mechanics and gravity at those unimaginable energies imprinted a slight deviation from this perfect pattern? Certain theories of quantum gravity, like loop quantum cosmology or some string theory-inspired models, suggest the chaotic foam of spacetime at the smallest scales could have subtly altered the fluctuations as they were stretched. This might manifest as a tiny, specific break in perfect scale invariance, a slight preference for certain sizes of cosmic ripples over others, or it could appear as non-Gaussianities, a technical term meaning the hot and cold spots in the cosmic microwave background would have more complex statistical relationships than a simple bell curve distribution. Finding these subtle statistical anomalies would be like discovering the artist's thumbprint on the edge of a masterpiece, a sign that the canvas itself had a texture that influenced the brushstrokes. Searching for these signatures is a monumental task, requiring exquisitely precise maps of the cosmic microwave background and the large-scale distribution of galaxies across the universe. It means analyzing billions of data points, looking for correlations so faint they are buried in cosmic noise. This transforms our entire perspective. Inflation is no longer merely a theory about our own universe's first moments. It becomes a potential bridge, a Rosetta Stone for decoding physics at energies 1 trillion times higher than any particle collider will ever reach. The entire observable cosmos becomes our laboratory, and the ancient light from its birth is our data. Every new, more detailed map we create is not just a better picture of our past, it is an experiment probing the fundamental grain of reality. The quest to understand our own origin story has unexpectedly handed us the tools to explore the ultimate unification of physics, using the universe itself as both the experiment and the result. Our story of cosmic inflation began by solving concrete puzzles of flatness and uniformity, but it concludes by confronting questions that have no easy empirical answer. The theory and its staggering offspring, the multiverse, carry a philosophical weight that reshapes how we see our own existence. If every possible universe is realized somewhere in an eternal, branching froth, what does that say about the one we call home? One perspective suggests a chilling diminishment. In an infinite ensemble where all stories are told, our particular narrative, with all its beauty and tragedy, becomes just one copy among an endless number. The grand epic of our cosmos, from the first stars to the rise of consciousness, is reduced to a statistical inevitability, a line in a script repeated infinitely across the metacosmos. It can feel like learning your cherished hometown is not a unique community, but a mass-produced template repeated on every street of an infinite city. This view sees the multiverse as the ultimate democratizer of reality, rendering our universe unremarkable by sheer abundance. Yet there exists a counterpoint, a perspective that finds not diminishment but profound wonder in the same mathematics. If the multiverse is real, then the conditions that allow for our existence are not a happy accident of a single, fine-tuned cosmos. They are the result of a ruthless cosmic lottery, a selection effect of staggering odds. In a landscape of 10 to the 500 possible vacuum states, the fraction that permits atoms, stars, planets, and life is unimaginably tiny. That we find ourselves in such a rare and hospitable bubble is not evidence of design, but it is evidence of an incredible statistical rarity. Our universe becomes a precious oasis in a desert of lifeless mathematical possibility. Its laws are not mundane, they are a winning ticket drawn from a cosmic hat of near infinite size. This shifts the question from why our universe is the way it is, to the awe-inspiring fact that we are here to ask the question at all. It suggests that consciousness, far from being a common byproduct, might be an exquisite and fragile phenomenon, glimpsing itself in one of the few corners of reality where such a thing is possible. This duality between cosmic humility and grandeur sits at the heart of the inflationary legacy. It pushes beyond physics into the realm of meaning. Does a theory that predicts countless realities make our own journey less significant, or does it render the fact of our awareness all the more astonishing? The answer may depend less on the equations and more on the story we choose to tell ourselves about our place within them. The silence we have heard so far is not an ending, but a call to build better ears. The profound questions left by inflation, from the nature of the Inflaton to the reality of the multiverse, are no longer purely theoretical. They are now engineering problems, driving a global race to construct instruments of almost unimaginable sensitivity, designed to listen for the faintest echoes of creation. The next decade will see a wave of technological marvels, each a monument to human curiosity, aiming to turn speculation into evidence. At the frozen, thin-aired heights of the Chilean Andes and the South Pole, a new generation of telescopes is rising. Projects like the Simons Observatory and the even more ambitious CMBS-4 are not mere upgrades. They are arrays of thousands of superconducting detectors, chilled to a fraction of a degree above absolute zero, designed to map the cosmic microwave background with a precision we can barely conceive. Their primary target remains that elusive curly signature, the B-mode polarization from primordial gravitational waves. If that whisper from inflation's first moment is there, these instruments will be the first to hear it. But their ambition runs deeper. They will scour that ancient light for the subtlest statistical anomalies, the non-Gaussianities or broken symmetries that could hint at the quantum grain of spacetime or the specific shape of the Inflaton potential. They are not just cameras, they are forensic scanners for the universe's birth certificate. Meanwhile, other eyes are looking not at the first light, but at its ultimate consequences. Enormous digital sky surveys are now underway. The Dark Energy Spectroscopic Instrument, or DESI, is already measuring the precise distances to tens of millions of galaxies. Soon, the European Space Agency's Euclid telescope and the ground-based Vera C. Rubin Observatory will join this effort, collectively mapping the three-dimensional structure of the cosmic web across billions of light-years. This vast cartography of the present universe is a direct test of the past. By measuring how galaxies cluster and how their light is bent by dark matter, weak gravitational lensing, these surveys can detect the imprints of those primordial quantum seeds with staggering detail. They can measure the exact statistical pattern inherited from inflation, searching for deviations that might tell us if the Inflaton field interacted with other unknown particles, or if something even stranger occurred in those first moments. And then there are the listeners for the ripples in spacetime itself. While ground-based detectors like LIGO probe the high-pitched chirps of stellar mass black holes, a new class of observatory is preparing to listen to a lower, more ancient hum. The Laser Interferometer Space Antenna, or LISA, is a planned fleet of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. It will open a low-frequency gravitational wave window on the cosmos. Within its reach could be the stochastic background, a steady sea of ripples from the violent chaos of reheating, or even from cosmic strings or phase transitions predicted by some inflationary models. Detecting this hum would be a direct probe of the universe's fiery transition from inflationary cold to Big Bang heat. These are not separate experiments, they are a unified campaign. The cosmic microwave background gives us the initial conditions. The galaxy surveys show us the evolved result, and gravitational waves could reveal the dynamics of the transition between them. Together, they form a triangulation of truth, aiming to pin down the story of our origins from multiple, independent angles. This global endeavor represents more than just data collection. It is humanity's collective effort to read the faintest whispers from the dawn of time, pushing the limits of materials science, cryogenics, and quantum measurement to answer the most fundamental questions we can ask. The mysteries that inflation created are not passive puzzles, they are active engines, driving the very forefront of scientific exploration and reminding us that our quest to understand where we came from is also a journey to discover what we are capable of building. The equations of inflation may live in academic journals, but their soul now wanders freely through our stories. A concept that began as a solution to cosmic flatness has become a wellspring for modern mythology, reshaping how we imagine possibility itself. You can see its influence in the kaleidoscopic narrative of a film like Everything Everywhere All at Once, where the premise of branching realities becomes a playground for exploring family, regret, and the weight of infinite choice. It pulses through the pages of science fiction novels where characters step between worlds, each with a different history, a different set of physical laws. This cultural embrace is not an accident. It is a testament to the raw, evocative power of the ideas themselves. Inflation gave us a scientifically plausible doorway to the multiverse, and storytellers have rushed through it, not to lecture on field potentials, but to ask the human questions that physics alone cannot answer. Who are we if every decision spawns another version of ourselves living a different life? What is the value of a single moment if it is just one note in an infinite symphony? These artistic explorations do more than entertain. They perform a vital translation, turning abstract mathematics into emotional experience. They allow us to feel the existential vertigo and the breathtaking potential of a cosmos without end. This is where science fuels the imagination, providing a new vocabulary for age-old wonders. Yet this beautiful synergy creates a delicate responsibility. For every rigorous exploration, there are a dozen more that use the word multiverse as a magical plot device, a hand wave to explain anything without the burden of rules. As we share these cosmic ideas, we walk a careful line. We celebrate the solid, evidence-backed framework of inflation, the maps of the cosmic microwave background, and the solved puzzles of flatness and horizon. We must also be clear about the frontier, distinguishing the well-tested core of the theory from its spectacular, but still unproven, consequences like eternal inflation and a vast multiverse. This is not about dismissing wonder, but about honoring the true nature of the scientific journey. The dialogue between science and story is ultimately a dialogue about meaning. When a physicist describes quantum fluctuations stretched to cosmic scales, and a filmmaker shows a heroine tapping into the skills of her alternate selves, they are both, in their own language, grappling with the same profound mystery. How does our specific, tiny corner of reality connect to something vastly greater? The cultural life of inflation shows us that cosmology is never just about distant galaxies. It is a mirror reflecting our deepest questions about identity, chance, and our own fragile, precious place in an unfolding story whose first chapter we are only just beginning to read. But a scientific theory is not a monument, it is a living conversation. For every elegant solution inflation provides, a chorus of thoughtful critics has raised profound and necessary questions. Some of the most respected voices in physics argue that the theory, in its most expansive forms, has strayed from the very essence of scientific inquiry. Their central charge is that inflation may have become untestable. If the multiverse predicts every possible outcome across infinite bubbles, then what observation could possibly contradict it? A theory that explains everything ultimately predicts nothing specific. This concern strikes at the heart of the scientific method, which relies on the possibility of being proven wrong. Critics also point to the remarkable flexibility of the inflationary framework. With hundreds of possible models, each with a differently shaped inflaton potential, the theory can be tuned or adjusted to accommodate a wide range of observations. If one model is ruled out by new data, another can often be crafted to fit. To some, this begins to feel less like a precise prediction of nature and more like a versatile story that can be retrofitted to the evidence, a framework so adaptable it risks becoming a theory of anything. Then there are the lingering puzzles we have already touched upon, the fine-tuning of the inflaton potential itself, and the mystery of its own initial conditions. Have we truly solved the universe's fine-tuning, or have we simply relocated the mystery from cosmology into the realm of particle physics? These are not dismissive attacks, but essential critiques from scientists who value rigor above all. Engaging with them is not a sign of the theory's failure, but a demonstration of science working as it should. This healthy skepticism acts as a vital immune system for cosmology. It forces proponents to sharpen their predictions, to identify which models are truly minimal and which are merely convenient. It pushes the entire community to design ever more clever and decisive experiments to find that elusive gravitational wave signal or statistical anomaly that could rule out whole families of inflationary scenarios. The debate itself, often lively and public, is a sign of a field brimming with ideas, where no narrative is so sacred it cannot be challenged. The ultimate fate of cosmic inflation will not be decided by who speaks the loudest or writes the most elegant equations. It will be settled by the silent testimony of the cosmos, through the painstaking collection of data from telescopes at the edge of the world and instruments in the quiet of space. The skeptical voice ensures the bar for that evidence remains astronomically high, guarding against the comfort of a story we might wish to be true, and demanding instead a story proven by the unforgiving light of the ancient sky. The story of cosmic inflation is a narrative of profound transformation, a single, fleeting moment that set the stage for everything that followed. It begins with a trigger we do not yet understand, a spark in the void that ignited an epoch of exponential expansion. In that sliver of time, smaller than any fraction we can meaningfully describe, the fabric of reality itself stretched at a rate beyond comprehension, solving the deep contradictions that plagued the old story of the Big Bang. The horizon problem vanished as regions now separated by billions of light years were once intimately connected. The flatness problem dissolved as any initial curvature was stretched into imperceptible smoothness. The missing monopoles were swept away into a cosmic vastness so immense they effectively disappeared from our local reality. And most beautifully, the random jitters of the quantum realm were magnified into the grand seeds of galaxies, planting the blueprint for all future structure. This elegant framework did not remain just a clever idea. It made a specific, testable prediction about the pattern of the universe's oldest light, a prediction that has been confirmed with stunning precision by our most powerful telescopes mapping the cosmic microwave background. The theory then culminates in the violent, creative chaos of reheating, where the stored energy of inflation erupted into the searing plasma of the classic hot Big Bang, filling the newborn cosmos with the particles and radiation that would become stars, planets, and us. Yet, in solving these foundational mysteries, inflation did not provide a final answer. Instead, it became a generative engine for even deeper and more expansive questions. The mathematics naturally suggests the possibility of eternal inflation, a process that never truly ends, giving rise to a potentially infinite multiverse of bubble universes, each with its own laws of physics. This breathtaking vision reframes our entire cosmic home as potentially one episode in a boundless, ongoing drama. At the same time, the theory pushes our understanding to its limits, raising profound puzzles about what came before inflation, how it began, and how its own parameters could be so exquisitely tuned. It forces us to confront the Trans-Planckian Problem, where our known physics breaks down, and to grapple with the philosophical weight of infinite realities. Inflation, therefore, occupies a unique and powerful place in our understanding. It is both a triumphant solution, providing the first coherent, evidence-backed narrative for the universe's first moments, and a brilliant provocateur, pointing beyond the edges of our observable reality to possibilities that challenge our very concepts of existence and uniqueness. It tells us that our cosmos is likely not a singular, isolated event, but may be part of a much larger, perhaps eternal, tapestry of becoming, leaving us with a story that is both magnificently complete and wondrously open-ended. This journey through cosmic inflation leaves us with a profound duality. We possess a theory of stunning explanatory power, one that has fundamentally rewritten the first chapter of our universe and given us a coherent, evidence-backed story for its birth. It explains the smoothness, the flatness, and the very seeds of all cosmic structure with an elegance that feels almost too perfect. Yet, in its success, it has opened doors to realms of speculation that challenge the very foundations of science and philosophy. We are left holding a map that perfectly charts the known cosmos, but whose edges fade into a terra incognita of infinite bubbles and quantum beginnings. The true legacy of inflation is not a closed book, but an open invitation. It invites us to look at the night sky not as a static picture, but as a dynamic, unfolding story whose prologue was more dramatic than we ever dreamed. It compels us to build better telescopes, to design more sensitive detectors, and to think with greater courage about what lies beyond our horizon. The quest to understand our origins is humanity's oldest and grandest story, and cosmic inflation has given us a thrilling new chapter, complete with its own unresolved cliffhangers. As new data streams in from the frontiers of observation, we may find that our current story evolves, or that a challenger rises to take its place. That is the beautiful, relentless engine of science. So the next time you gaze up at the stars, remember you are not just looking at points of light. You are seeing the magnified quantum whispers of a single, transformative instant, and you are witnessing a mystery that is still being written. If this exploration of the cosmos's first moments expanded your perspective, we would love to hear your thoughts in the comments. For more journeys to the edge of understanding, subscribe and join us as we continue to look up and look back toward the universe's greatest secrets.